Okay, welcome to the EJ's rocket launch and rocket testing review. So we got two things going on here today. This is the 26th of June, 2025. We got two events happening. We got the rocket launch, get the hawk out of here launch, and then we have Northrop Grumman's booster obsolescence and life extension program. It's an SRB test fire that should be happening soon. The first thing that's teed up here is the Rocket Lab launch. We're at T-minus 11 minutes and 13 seconds, and we will key the audio right in here.
There you have it. We are a go for today's Electron launch, and the countdown continues. We are on track for an on-time liftoff at 5:28 a.m. local time, still well before sunrise here in New Zealand. And we've got two T0 opportunities today, so if there's a delay for any reason in the remaining minutes to launch, then we've got a second chance to try again later in the launch window. So far, though, no watch items for the rocket, payload, or range clearance, so we are tracking nicely to schedule for an on-time liftoff.
Okay, so this is the Get the Hawk Out of Here launch. It is launching a Hawkeye 360 cluster number 12. Hawkeye 360 is a part of a bigger satellite constellation. It's 15 satellites in 5 different orbits. 5 shells is what they're called. Aims to deliver precise mapping of radio frequency emissions anywhere in the world. There's 3 of them for this shell. Yeah, we got 15 satellites total, 5 shells, 3 shells per. Total payload mass is about 90 kilos. That's about 200 pounds of 3 satellites. There's also the Kestrel 0A demonstration mission. It's another one of Hawkeye 360's new spacecraft design. So Kestrel 0A differs from previous satellites in that it has an 8U CubeSat form factor, so it's a little bigger, actually, than the other ones. If I'm reading that right. And we'll have an Iridium satellite transceiver for communications between the satellite and the ground network via the Iridium constellation. That one is 15 kilos, or about like 35 pounds. So yeah, looks like they're launching out of LC-1A at the Mahia Peninsula in New Zealand. And it is their 9th flight of 2025. That's pretty good, man.
That all have to come together.
My name is Anita Becerra, and I'm the Senior Supervisor of Space Systems Production. I have a highly skilled team that allows us to produce spacecraft at scale. What's great about Rocket Lab is that everything is...
We can't listen to this. It'll mute. Anyone's B-roll footage always mutes the VOD. Those numbers are pretty good, man. Yep. 9th mission of 2025, 67th mission total. Rocket Lab is scaling. It's pretty good. Slowly but surely, they're getting there.
Spacecrafts leave our building.
All right. See, Rocket Lab is also positioning themselves as basically what, like the automobile industry equivalent of a AAA manufacturer. They make satellites, they make bespoke satellites, they make one-off parts, and they're supplying them to other companies that need them, like re-entry capsules from BARDA, for instance. Control moment gyros, thrusters, all kinds of stuff to be able to bring the cost down of making satellites, so more people can launch on their rockets. Even then, Rocket Lab doesn't need, even if you're using Rocket Lab parts, though, that doesn't mean you need to launch on their rockets. They make parts for everything, all different types of satellites that have launched on all different types of rockets. It's actually super cool. Really, really good manufacturing pornography going on here. Hey, Stevio, what's up? I hate that because this is like free advertising for them. You'd think they would want as many people to replay the video as possible. Didn't Blue Ghost have Rocket Lab parts on it? Yes, Goatman, it did. Also, don't forget to do the ads. Yeah, we'll run pre-roll ads. We'll do an ad break now on Twitch, so nobody gets pre-roll ads during the launch. I hate running ads, but it would suck even more to get it right in the middle of a damn rocket launch. Now on YouTube, I don't have control over that, so if you get an ad during it, I'm sorry. It's not Rocket Lab that claims the music. They've licensed it from a third party, and they have permission. They paid for the license for it, but I didn't. So, even though you could argue that their background music is transformative, right? That's not how the music industry works. So, it's fine. It's not worth arguing. We can watch this video later. Or I'll watch it and convey everything that he's saying to you. Yeah, there you go, Dan. Here, you know what? I can mute it and I'll just say what he's saying. And right when I did that, they shut it off.
Very cool. And as you saw, lots of spacecraft and hardware with
Oh, yeah, it was really good.
logos on them. Even the satellites on today's mission will be deployed from a motorized light band separation.
Ship watching, hello. Should you go touch grass immediately?
To safely and reliably patch the satellite from the rocket in space. Now, we
Yeah,
are at
sure.
T-minus 4 minutes, 43 seconds and counting on the clock, which means we are heading into the final moments before liftoff to get the Hawk out of here. Here's how those final few minutes are expected to play out. So first up, at T-minus 2 minutes, you'll hear the call that Electron is on internal power. And this means Electron is now running on its own power supply. More importantly, though, it also signals that Electron's flight computer has taken over the reins for the final pre-launch sequence.
Now, after that, we'll hear a call for AFTS, which stands for Automated Flight Termination System. And this confirms that Electron's onboard safety systems are fully active and its telemetry systems are verified to be transmitting data back to mission control. After that, expect to hear confirmation that Electron's liquid oxygen propellant, or LOX, has been loaded and that it's circulating within the vehicle. And then after that, a call should come that Electron's tanks are pressed for flight, and this means that the propellant tanks are fully pressurized, locked and loaded, and ready to unleash the power of Electron's Rutherford engines.
Interesting.
What
Mike.
follows should be a call that high-flow engine purge is enabled, which will mean that the Rutherford engines are primed and ready to ignite. And then last but not least, our launch director will remind operators of their position in the countdown, usually at around 20 seconds to launch, right before taking us down through the final 10-second countdown to liftoff. So let's bring up the audio channels from Mission.
What's Dragon's new name? They named the last Dragon 2 capsule Grace. Yeah, do with that information what you will.
To all operators, from now on, there should be no red flags in your critical LCCs. Beacon LD on mission card.
LD Beacon.
Please lock the auto sequence and confirm.
Locked.
And please confirm all flight computer ASGOs are green.
All ASGOs are green.
Copy. We are go for auto sequence start at T-minus 2 minutes, and LD is go for launch.
No, Grace, not race. Grace. Are we going to watch the SRB test after? Oh, yeah. Look at the title, man. It's not the EJ's Rocket Launch and Rocket Testing Review for no reason. Yeah, go ahead, Mike.
The vehicle is fully on internal power.
Okay, we're inside of 2
AFTS
minutes.
is green and enabled for flight.
T-minus 90 seconds.
LOX load is complete. System is in recirculation. Anti-geysering is disabled.
Inside of 1 minute. What fuel does Electron use?
Stage 1 and 2 tanks are pressed for flight.
RP1 and liquid oxygen. That's why the
High flow engine purge enabled.
the lighter parts of the rocket, it's actually not white paint, and that's ice. You'll see it come off the vehicle when it flies here. "30 seconds. 30 seconds remaining.
T-minus 20 seconds and counting.
15.
10, 9, 8, 7, 6,
Sound
5,
suppression water system is on.
4, 3,
Ignition.
2, 1. Liftoff.
And we got a liftoff of Get the Hawk Out of Here! Launching 4 satellites for Hawk 360. I'm not gonna make a joke. I'm not gonna do it. I'm not doing it. I'm not doing it. I'm not doing it. There's all the ice coming off.
Stage 1 propulsion nominal.
Just gotta launch on that thing. You gotta give it a little hawk.
Damn it! The Hawk
Damn
is
it!
out of here for Electron's 67th launch.
Sorry, I couldn't help it.
Spectacular liftoff for Electron, and that fiery plume lets us know that we are climbing fast, and soon we'll be reaching maximum aerodynamic pressure, also known as max
I knew you
Q,
could do
as Electron punches through the atmosphere. Our launch ops team and mission control will be calling out that critical moment shortly, so let's listen in.
Electron is supersonic, approaching max Q.
Looks like the clouds are what's making that go. Either that or something's broken. No, telemetry still seems okay. That's just the clouds. The intrusive thoughts one.
Cleared max Q.
Couldn't help it, Indy. Couldn't help it.
There we go. Confirmation from Mission Control that we have cleared max Q. Right now, Electron is moving at over 2,000 kilometers an hour and past an altitude of 20 kilometers. And our next launch milestone will be MECO, or main engine cutoff, in just under a minute and a half. What that involves is 3 critical actions across Electron's first and second.
Rocket guy, weather guy. Can you check the cloud cover for Mahia here? That was a lot of clouds. Unless the cloud cover goes up to like 30,000 feet from like 3,000 to 30,000. Something might be wrong with the camera.
On its way
hopefully
to
not
orbit.
the rocket.
So let's listen back into Mission Control to hear those 3 crucial calls.
Go in roughly 30 seconds.
"15 seconds to staging."
I mean, it looks fine now.
Enter burnout detect mode.
10 seconds till main engine cutoff.
MECO confirmed.
Stage separation confirmed.
Stage 2 ignition confirmed.
Yeah, no, everything's fine. Everything's good. That staging
And
was
there
great.
you have it from Mission Control.
Perfect.
We've confirmed a successful main engine cutoff. We love to hear that. Now, next up, we'll be seeing the fairing jettison, where Electron's fairing halves actually split apart and fall away. So keep your eyes peeled on your screen for that one coming up soon.
Fairing separation confirmed. It'll be in another couple of seconds here.
Descent
Or-
confirmed.
Okay, weather guy.
And you just heard it there from Mission Control, a lovely fairing jettison.
Lovely.
You can see Hawkeye 360 is well and truly on its way to orbit, now travelling at 8,500 kilometres an hour, just passing 125 kilometers in altitude. What a ride for these 4 satellites.
HVB discharge holding nominal.
We'll see, Marcel. Yeah, just the cloud. Yeah, okay. I see it well again. Thank you.
Guidance is looking nominal so far into the mission, which you can track in real time with the trajectory plot that will show up on the right-hand side of your screen soon. Otherwise, the total burn time for this second stage engine is around 6.5 minutes to take us all the way to a nominal transfer orbit.
They're right down
now,
the
the
pipe,
stage 2
dude. The
Rutherford engine
trajectory's
is
spot on.
practically identical to the stage 1 engines on the booster, apart from an expanded nozzle that helps to maximize the thrust from Rutherford
Yes, they do,
and
Shiv.
improve its overall performance. And we are now at T plus 4 minutes, 32 seconds into the mission, with expected engine cutoff at around T plus 9 minutes.
Alrighty, next up in Electron's series of maneuvers is the battery hot swap, a move that's unique to Electron, given that its second stage Rutherford
They're a
engine.
little ways out from jettisoning this. Basically, because they are using electronic fuel pumps, they have a battery right here. The battery gets jettisoned once it runs out of charge. You'll see it. You'll see. It'll be quick though, but we're still a little ways off. Methane subcooler. What's the TWR on Electron? At liftoff, probably like 1.2, 1.3. It goes, man. She goes pretty quick. What is the payload? We got 4 satellites on board, 3 operational satellites and 1 prototype satellite for a company called Hawk 360. Hawk 360, hence the name of the mission. Hawk 360 is a radio. It says I got to read this off the card because I wasn't sure. Hawk 360 is a radio frequency geospatial analytics provider. Interesting. They have a satellite constellation. They're building out a satellite constellation comprised of 15 satellites and 5 shells. 3 satellites per shell.
Throttling down.
Okay, watch. The battery's going to jettison here. Interesting, Kyron. Nice.
Battery jettison confirmed.
Here it goes. Bye-bye.
An excellent battery hot swap that we saw there, and we heard from Mission Control as well. So we are now at T plus 6 minutes, 40 seconds into the mission, with Electron boosting along at more than 15,000 kilometers an hour.
Okay. Once this thing gets to kick stage separation...
T plus 7 minutes into this mission, you can have a look on the right-hand side of your screen. Our propellant levels are consistent at 29% remaining for kerosene and liquid oxygen. Our kerosene temperature sitting at a balmy 12 degrees compared to our liquid oxygen temperature of negative 177 degrees Celsius. And
the batteries will... Clever girl, you love dropping batteries in the ocean. They're going to burn up. Second stage is going way too fast for those things to get down in one piece. The batteries will burn up in the atmosphere. So do Falcon and Electron use the same fuel? Yes. When neutron? Probably early 2026 EVGBs if I had to bounce a betting, man. Is that fuel gauge new? Yeah, relatively. Yeah, I think they started putting that in like 1 or 2 streams ago. I like the trajectory one that they have. It shows how good the rocket's flying. And from their trajectory overlay that they did put on the screen, the thing was flying right down the pipe.
We're now nearing the end of the second stage's journey with SECO, or second engine cutoff, right around the corner. So soon, that single Rutherford engine powering Electron will shut down, and the kick stage will seamlessly separate, carrying Hawkeye 360's satellites where they belong on orbit. So let's chuck it back to Mission Control for that critical call now.
Guidance is in terminal, 25 seconds remaining.
Onboard audio, question? The first stage makes it back down ship, yes. But they don't recover it. That's why they're building Neutron, so they can fix that
Seeker
problem.
confirmed.
Okay. There it is. 28606
Stage
at
separation confirmed.
203. Yeah, that's fine. 28606 at 203. That's actually fast, so
And
that's an eccentric
there
orbit.
you have it. Mission Control has confirmed Seeker,
All right.
and the kick stage with its Hawkeye payload is now in its initial coast phase around Earth. And it will be another 40 minutes or so before the Curie engine on the kick stage ignites to make its final and
a good
precise
idea, David.
adjustments
Yeah.
to place
You're
Hawkeye
first.
satellites to a 520-kilometer circular orbit.
That's what I mean about the staging velocity being fast. There's 28606 at 200. That means the orbit is slightly egg-shaped with one point being higher than the other. And Muriel just said that the high point in the orbit is 500. So 28606 is an eccentric orbit. With the lowest part of the orbit in a park, like at a parking altitude, and the highest part of the orbit at deployment altitude. Cool. Well, while that's doing its thing here, that seemed to be a good insertion there. While that's doing its thing, we'll switch over to BOLE coverage. But I will keep that going in the background. BOE is delayed again. Uh-oh. Yep. 3518. What would the purpose be of this kind of orbit? Sun synchronous is what it's called, Surat. Actually, that one, let me go look at it again. Let me see what the inclination is. So they launched basically due southwest out of New Zealand. That is sun synchronous. That's an SSO orbit. 97, technically slightly retrograde. 97-degree inclination at 550. So that's sun synchronous. Sun synchronous orbits use Earth's precession, like natural occurring precession, to slightly adjust the longitude of ascending node of your orbit every time you go around. Because Earth's, so what's precession, all right? A little bit on orbital mechanics here. So what is precession? Earth is kind of a sphere. It's kind of not. It's more like a big spherical jello mold that's spinning really, really fast, right? And because it's not, Earth obviously isn't solid. We know that, above the crust right here, right, or below the crust, you have the mantle, and the mantle gets to the core. The core is made out of iron and nickel, and it's actually not solid because gravity is creating so much pressure at the center, right? It's actually molten. And because of this, the Earth's core kind of churns and bubbles around. And that heat gets dissipated through the mantle of the planet, right? And we're floating on the cool crust of the cooled off crust of the planet, right? But that means Earth's center of gravity kind of moves around because everything's on fire. Yeah, everything's molten, everything's really, really hot. So that's what I mean when I say that Earth is a gigantic spinning jello mold, right? You see. And that's part of the reason, because everything is churning and bubbling. That's kind of part of the reason why we have plate tectonics, right? Why, you have like the San Andreas Fault. The crust kind of collides into each other because Earth is constantly churning up and spewing up new material from the center. Like, and volcanoes are part of that process as well, right? Volcanoes are the cracks between two plates, right? Usually, right? The cracks between two plates that spew up the ejecta from like the center of the planet. Now, why do I mention all this? What the heck does that have to do with orbital mechanics, and why does that have to do with this orbit? So, because Earth's center of gravity never kind of stays at the geographic center of Earth, right? So if you cut Earth right in half, the center of gravity is a little bit, it's kind of offset, and it kind of weeble wobbles around, hence big spinning jello mold, right? You can use that spinning, the offset center of gravity of the planet, you can use that to change your orbit. Because when you're on one side of the planet, you're technically a little bit further away from the center of gravity. It's just a smidge. It's not a lot, but it's just the smidge, right? Like if this point right here is the geographic center of Earth, the center of gravity is over here somewhere. It's offset. So that's the other reason why Earth kind of weeble wobbles around about its axis, right? You can use those gravitational perturbations to actually change your orbit. A sun-synchronous orbit, which is around 550 kilometers at 97 degrees inclined, uses this phenomenon to shift the orbit. It shifts it slightly, altering what's called the longitude of ascending node. So the orbital track kind of moves a little bit around. With a sun-synchronous orbit, you basically can get a satellite going over the same spot at the same time every day. Now, think about like the ISS. The ISS isn't sun synchronous. So, the ISS kind of goes over our heads a lot, right? But we don't, you don't see it all the time. You'll see it at different times. Sometimes the ISS goes over at night. Sometimes it goes over during the day. This type of orbit gets around that problem. That makes it so if you have an Earth observation satellite, like what Hawk 360 does, or if you're the National Reconnaissance Office and you want to snoop on somebody's launch site, but, obviously trying to take a picture of the launch site in the middle of the night is not going to work. But you also want to make sure that you have constant eyes on it, right? So what do? You put a satellite into a type of orbit where it always goes over your boy's launch site at the same time so you can take a picture of it. Sun synchronous. These types of orbits are really, really useful for Earth observation satellites because the offset center of gravity of Earth will move the satellite so it gets into the same spot. It flies over the same thing at the same time every day. Is it possible to get to the ISS if you launch any place from Earth? With enough delta V, you can get anywhere, Linus. Generally, though, the ISS is in a 51.6 degree inclined orbit. It would be exceedingly difficult to get to it anywhere north of 51 degrees latitude. Get anywhere near north of 51 north and 51 south, because it's in a tilted orbit, so it kind of, if you traced its ground track, it kind of goes like this. The reason why they put it at such a tilted orbit is so the Russians, us, the Japanese, and the Europeans can all get to it. Don't take this the wrong way. I mean it friendly. Hey, screw you. You've gotten much better at explaining this sort of thing to space to ignorant people from when I first joined. Age like fine wine, baby. That's my goal. I fully understood that. I didn't know the two centers were different, and it makes sense. When you said everything's on fire, I felt that. Oh, yeah? They have a new prototype for the constellation? Yeah. They're carrying 3 operational satellites, Raiden, and 1 prototype for their next generation constellation. It's called Kestrel 0A. It's an 8U CubeSat. I got all this information off Next Space Flight, if you're wondering. Not sure if you got this earlier. Fluffy, I did, but I was watching the launch. I saw what you said. Vulcan is planned for a lot more launches this year. All right. Maybe you should finish the building that they need to finish the building that they build it in before they do that. 14 launches is a little steep, but you got to remember, ULA is trying to scale. ULA had a business model that was centered around maybe launching once or twice a year. All of a sudden, Project Kuiper and the launch market demand changed drastically, right? The launch market changed so much that they had to readjust their business model. The only way they could really do that is after capital infusion. So, i.e., after the Project Kuiper block buy of ULA launches, they bought 38 Vulcan launches. And now what ULA has to do is scale. Scaling is difficult, especially when your business model is kind of centered around building one rocket building one rocket a year, maybe 2 rockets a year. So yeah, they have the provisions for 14, but scaling is difficult. Just to kind of take it back to stuff that we've talked about before. That's why SpaceX doesn't want to take their foot off the gas, and that's why they want to keep launching ships despite them knowing that they could pop. Because slowing down your production capacity is very difficult to speed up again. Do you think they underestimated it a little bit? Yeah. Yes, absolutely. Okay, and I don't mean this to disparage or denigrate ULA in any way. I like Tory Bruno, and I like United Launch Alliance, and I think Tory Bruno has done a fantastic job in the 11 years that he's been a CEO. The CEO of the company, he's amazing. What do they know about scaling? I mean, clearly Tory Bruno knows something, because they're scaling and they're working on it and they're getting there. We've seen more Atlas launches this year than we have in like the past 4. No, that's not exactly true, but you get the idea. The frequency of launches from them is picking up. So that's good. That's real good. They'll get it. It's just going to take a little bit longer. Now, I will say this. I think Tory Bruno knows something about scaling up. He did work on the THAAD project. I don't know if you guys have been keeping up with current events. People are launching ballistic missiles at other people, and they're getting popped in midair, high altitude intercepts. That is a project that Tory Bruno actually worked on. It's called Terminal High Altitude Area Defense, THAAD for short. It is a ballistic missile intercept rocket. And they made a lot of those. We know they made a lot of those because we see a lot of them being used as of late. So Tory Bruno does know something about scaling. It's just trying to retool a company that's designed for 1 to 2 launches a year to even 15. That's a big thing to ask. You can't go from launching 1 to 2 rockets a year to launching 15. Not even SpaceX did that, right? SpaceX went from launching Falcon 9 once a year to launching it twice a year to launching it 5 times a year, and then to 10, and then to 15. But even then, in 2019, when they were scaling for Block 5, we saw them expend a bunch of Block 4 boosters, right? And then in 2019, we saw the launch rate dip. We saw it go down. Only time Falcon 9 launch rate has gone down comparatively to the past year. Scaling takes time. And we haven't seen a lot of launches from ULA, except as of recent with the KA-01 and KA-02 missions, which means they're about ready to open the floodgates. So I'm not sure we're going to see 15 launches from ULA, from Vulcan, for the rest of the year. I would say probably 5, maybe 5 to 6. Next year, though, I'd believe that. Sure, absolutely. Easy. Next year, yeah, they'll probably launch it 20, 30 times. I mean, Bizak, that's not really what I'm getting at. I'm trying to tell you what's going on in the rocket industry, agnostic of political bias in one way or the other. Dude, respectfully, I don't want to talk about that, homie. I don't want to talk. You can talk about, if you want to talk about THAAD, sure. You know, I'll tell you, that thing is actually super cool. Super cool piece of kit, but trying to not bark up that tree, you know what I mean, dude? You know, you just had to get it out. Sorry, yeah, I hear you, man. Sometimes you got to. Sometimes you got to say what you got to say. Thanks for being cool about it, man. But yeah, I mean, there's plenty of other streams where you could talk about that, dude. I don't want to be one of them, man. I'll talk about the tech, sure. But yeah, anything else, I don't know. No. I don't want that. You've watched an intercept happen live. Yeah, Nick, it's pretty cool. Pretty cool piece of technology. What is the status of Oli? Aww. Now, I've always wondered, why don't they have space observation satellites, telescopes, either at geosynchronous or Lagrangian points? You spelled Lagrange fine. Why, Sewer Rat? When you have that sun synchronous orbit? So, okay, here's another cool thing. You know, okay, let's put a telescope at geo and look down. Sure, yeah, that could work. With sun synchronous orbits, you can use those same perturbations, that same precession, right? You can use the same precession to switch where the satellite flies over. Slight adjustments in timing will throw you out of perfect sun synchronization. So, say you want your satellite to look at an airfield on one side of a really long country, right? Have the satellite desync its orbit. It'll go out of sync for a second and then resync it over another point. With sun synchronous, dude, they can look at anything. They'd look at anything. You can look at anything you want. You just got to change the timing of the orbit slightly by increasing or decreasing apogee or perigee. Or you could just decrease perigee and use some aerobraking, natural atmospheric perturbations to go out of sync and then resync later with thrusters. Pretty cool, huh? So basically, what I'm trying to tell you is that they can see whatever they want. Earth observation satellites can change. They can move. If it's a spy satellite, it could go anywhere. It could look at an enemy airfield, or it could look at an enemy mountain, or it could look at a port or a city or whatever. You can change it. I meant for space and deep space observation. I think like Hubble and James Webb. Well, James Webb is further than GEO. James Webb is in a spot with as low a sunlight as possible, but it's still close enough to where we could, communicate with the dang thing. James Webb is at a Lagrangian, is at Earth Moon L2. Or no, is it Earth Moon L2 or Earth Sun L2? I think it's Earth, no, it's Earth Moon L2. It is. So it's called EML2. James Webb is at a Lagrangian point, dude, if that's what you're asking. Can you put Twitch chat in a little box, please? I don't like having the chats on the screen, Sintesi. The only way I would really want to do that is if I could have both chats, but Twitch doesn't like it if you have both Twitch and YouTube. So, I mean... We'll just keep the Rocket Lab thing up for the time being. So then why was Hubble in low Earth orbit? Because Hubble is an Earth observation satellite that's pointed in the wrong direction. Why do you think they needed to put glasses on it? Because it's nearsighted. Does that make sense? It's not. The Hubble is a highly modified Earth observation satellite. But because there were people working on the lens that weren't used to making a satellite be far-sighted, so to speak, as opposed to near-sighted, they gave it the wrong prescription, so to speak. Because the Hubble was so big, and because it was technically an off-the-shelf component that was already designed to fly inside of the space shuttle, it was an easy win to just take one of the satellites and modify it for Earth observation instead. And because it launched on the shuttle can only move it so far. So that's why Hubble is in low Earth orbit. James Webb is designed for space observation from end to end. The Hubble is a highly modified, I think it's a Keyhole 9, or no, maybe a KH-11. It's a spy satellite with it's a very, 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 very hot-rodded spy satellite that's pointed the wrong way. KH-11, yeah, thank you. Yeah, Sarah, it's against terms of service technically, but you know, you never know what you can get away with, you know what I mean? Like, just because you see other people doing it doesn't mean that you're not going to get zapped for doing it as well. And then, you know, if you do get zapped and they get mad at you, right? You can't be like, well, that guy's doing it. That usually doesn't work. Are there planned telescopes to be further out? Look up the LUVOIR mission. LUVIOR. Yes. That's right, Raiden. Mm-hmm. Is the Nancy Roman Space Telescope a modified SpySat too? Yes. LUVIOR. Surat. The same reasons that, yeah, exactly. Nancy Roman's not going further than Leo. Yeah, spoiled, but I don't want to be the one to do it. You know what I mean? Yeah, I got you, Denny. I asked that guy what's wrong with NSF. Should I tell you what he said? No. No. You didn't have to do that. No, but don't worry about it. Ship, don't worry about it, dude. Not everybody's gonna like what NSF does, dude. That's fine. I'm not. We don't need to go being like, what? Like, don't worry about it. I read what he said. I'm not that hopeful in new space projects because funding. Just a bump in the road, Wombat, it'll come back. Is BOLE carbon fiber? Yeah, it's a carbon composite booster. It's not exactly fiber, it's composite. I'm not sure if fiber would be able to withstand the pressures involved here. Is this an upgraded SRB? That's what the Booster Obsolescence and Life Extension program is all about. Upgrading. These are the Block 2 SLS boosters, guys. That's if you really want to know. There you go, Dons. I love the twinkly space music. I do believe that this is Tim's music. This is Everyday Astronaut. Rocket Lab uses them. Tim, excuse me. Hope there isn't an observation observed during the observation of this firing. Me neither. The last time Northrop Grumman tested a carbon composite booster, there was an observation. The nozzle exploded. But that's because it was vacuum optimized. Is it Tim Boy, the Astro Dodd? Yes. Yeah, Tim is a very good composer. Believe it or not, yeah. Guy's the real deal, man. Plays the guitar better than I do, dude, that's for sure. With that being said, I'd love to jam with him at some point. Give me 1 second. He said he would have done music as a career if he hadn't run face first into rockets on the way. He's good, man. Guy can play. He can jam, dude. There's videos of him shredding on a guitar out there. It's pretty good. You and Tim should co-stream Artemis too. I'm not sure I'm worthy of doing something like that, Neptune. I'm not sure. That's like playing in the big leagues, man. I'm a minor league commentator, dude. I'd do it if he asked. Like, hell yeah, that'd be sick. Definitely. Just noticed your hat. Hell yeah, brother. That's right. Sorry, I had a hangnail. I had to get rid of it. It was pissing me off. Now your knowledge is up there and converting it to space noobs. You should send your Flight 5 booster catches or application. I mean, guys, if you look at it like that, I'm with NSF. That's pretty dang good. I'm too busy streaming here to do commentary with them a lot. I want to do more. There's just not enough time in the day. Were you thinking of going down to the Cape for Artemis 2? For your stream or for NSF? I haven't even thought about it. Artemis 2 is so dang far away, Fluffy. Ask that question again in 2026, man. Hopefully you're still here. Hopefully I'm still here. Oh.
Secondary bunker safety jumper indicate shows in. Evacuate to the instrument room.
Evacuating to the instrument room.
Close and secure the forward bunker door.
Worm logo. Worm logo. Worm gang. Are they broadcasting in 16:9 at 480? Okay. All right. This is a government-ran operation, sir. Budget cuts. I guess so. budget cuts were rough. I'm telling you, Jared, NASA should have their, like, a Hollywood tier, like, production team for these streams, man. Budget butts. Don't talk about my butt. That's weird. They have no idea how to broadcast to the public or promote NASA projects. You'll get no argument from me. You know what's really bothering me? The S and the first A in NASA don't line up. See that? With this NASAization font, with this style of font, that's not supposed to be there. It doesn't line up, and it's very, very, very frustrating. The S is too low. I'm sorry. It's if I have to deal with it, so do you. I'm sorry. It's just a personal hell of mine. Like, bro, somebody looked at that and said, "All right, that's fine. Yeah, that's fine." Is it maybe it's due to the 480p? Why would you do this to us? Why would they do it to me? Well, who's they? What do you mean the rebels blew up?
Room stray voltage checks are complete.
Roger. Instrument room, have the arming crew inspect the instrument room fire control safety jumper.
Worm. Cryo.
The instrument room fire control safety jumper is acceptable for use.
Roger.
You're right, William. The N is too big. The A and the S are at different altitudes, and that A is too low. None of them are lined up. It's
T-minus 15 minutes.
actually
Instrument room, have the arming crew install the instrument room fire control safety jumper.
Installing the instrument room fire control safety jumper.
Prepare to fast forward. Preparing to fast forward. Fast forwarding, sir. Fast forwarding.
Instrument room fire control safety jumper is installed.
The primary and secondary instrument room safety jumper indicates show in. Instrument room, have the arming crew install the instrument room fire line key and rotate to the closed position.
The fire line key is installed and rotated to the closed position.
Okay.
The primary and secondary T97 key switch indicates show closed.
Arming preparations are complete.
Evacuate to T22.
Evacuating the instrument room.
See, I don't mind this. I don't mind them piping the cast, or piping the communications loops in. That's fine with me. I just really would like a picture of what they're talking about. You know? Cars are leaving the area now. Yep, they just said evacuate to T22, so people should leave. They're leaving the instrumentation room. They could do this. I think Jack is controlling this camera. Also, the camera is crooked. That might just be the angle, though. Looks like it's tilted slightly that way. It looks like Jack might be trying to fix it here. So where is this test happening, dudes? This is in Ogden, Utah. It's near Promontory Point, which if you're a train buff, you know that area. It's where the Golden Spike was driven to complete the first transcontinental railroad. This is Northrop Grumman's SRB test facilities are super close to that. So this is up in the mountains in Utah here, and that's where they test it. They test in a very remote part.
7, 6, 5, 4-stage engine start. 3,
They gonna
2,
cut it?
1.
They cut out the boosters in ignition. Booster. What is the expected thrust of this booster? 14,000 kilonewtons, 14 meganewtons from one of these things. They're pretty powerful. These composite ones actually might even be a little higher.
Hi everyone, I'm Megan Carter, Media Specialist for NASA's Space Launch System rocket. As teams at NASA's Kennedy Space Center in Florida are busy getting ready for the first crewed Artemis mission, work continues all over the United States to prepare for future missions as well. One of those locations is right here in beautiful Promontory, Utah, at the Northrop Grumman facility, where I'm coming to you live today. Our partners here at Northrop Grumman have been working to develop a more efficient, lower-cost commercial solution for the boosters for the Space Launch System. As you can see, it is a beautiful day here in Utah, and we are actually just a few minutes away from a hot fire for the demonstration Motor 1 test.
Pretty bright.
The booster motor for today's hot fire is actually locked up on that hill in the test stand right behind me, and it's just about ready to be fired up. The boosters for NASA's moon rocket are the largest, most powerful that have ever been built for flight. And there are 2 boosters that flank either side of the rocket and together produce millions of pounds of thrust at launch. Today, we will get to witness the power of just one of those boosters. But before we kick this off, we're actually going to turn it over to Alyssa Lee in Huntsville, Alabama at Marshall Space Flight Center to learn a little bit more about what we're going to be seeing today.
I am very excited to be here at NASA's Marshall Space Flight Center with a resident SLS and booster expert. Joining me today is Julia Codobande, the Deputy Manager for the SLS Booster Element Office. Thank you so much for joining me, Julia. We are less than a year away from the launch of Artemis II, which will see SLS and NASA's Orion spacecraft on the first crewed mission for the Artemis campaign. So, would you be able to give us a little quick update on the progress for Artemis II?
Yeah, so Artemis II is currently being stacked at the Vehicle Assembly Building at Kennedy Space Center in Florida. So the twin solid rocket boosters have already been stacked, and the core stage with its 4 RS-25 engines has also been mated to the boosters. We have the Orion stage adapter here at Marshall Space Flight Center ready to ship and be integrated with the vehicle as well. Orion is currently being processed at KSC in the multi-payload processing facility. It's getting its propellants, its consumables, and the launch abort system, and once that's complete, it'll be ready to be delivered to the vehicle assembly building to be stacked onto the SLS rocket as well.
Wow, that's so exciting. It's going to be here before we know it. So as your role as a deputy manager for the booster office here,
Artemis 2
what
was
does your
supposed to
job
be in
entail?
2022.
And with that, what are you most looking forward to out of today's test?
So yeah, as Deputy Booster Manager in the Booster Element Office, we are part of the SLS Program Office. And my responsibility is to advise and to assist the Booster Manager in things like programmatic and fiscal and technical planning, procurements, contract actions, DDT&E, design development, test and evaluation, as well as production and operations of the booster. And this is going to include all of the support equipment as well as the facilities that are needed. What I'm most looking forward to today kind of goes a little bit back into history. When we started the SLS program, in order to save cost and schedule, we implemented the shuttle's proven heritage hardware into our design. But this is being depleted as the Artemis program progresses,
About
and
that
it's just
cost
not
and schedule
practical
thing.
to restart the manufacturing from that 1970s era. So for the last several years, we've been developing what we call the Booster Obsolescence and Life Extension, or BOLE. And so the BOLE is actually implementing new manufacturing processes and new materials from domestic sources.
Hey, FYI.
And so this test today is going to be the first full duration, full-scale test of the BOLE motor, which we're calling DM1 or Demonstration Motor 1.
So how does that tie into the goals and objectives of the test today?
So our goals today are to take a look at the performance of the BOLE motor. We are going to be looking at things like the ballistics performance, so the pressure and the thrust versus time, the burn rate of the motor, the pressure drop, the ignition characteristics. We're going to be taking a look at the performance of the internal insulation of the motor in the case acreage and dome areas. We also have a new carbon fiber composite case, which will be taking a look at its performance during the test, as well as the joints and the seals. We'll be taking a look at our nozzle ablative performance and the electronic thrust vector controls vectoring of that nozzle. And one of the other things that we're demonstrating with the BOLE DM1 today is that we're able to produce that next generation motor that is high performing, addresses our obsolescence issues, and does it more efficiently and at a reduced cost, which we are realizing a 25% reduction in cost. But going forward, any SLS booster or commercial solid rocket booster is going to need this next generation design because of the obsolescence issues.
Great, thank you, Julia. That was very enlightening, and I am so pumped to see this thing fire. Speaking of, I think it's time we check back with Megan in Utah to see if we are getting close to this big event.
Thanks, Alyssa. We are now less than 5 minutes away from the hot fire. We're going to take a quick break, and I'm going to get into position to watch. When we come back after the test, we'll actually be answering a few of your questions that were submitted in the chat. But for now, let's get ready to fire this booster up. Just before the test, you are going to hear a countdown from the test conductor, followed by the 2-minute booster firing. Enjoy. We'll see you back here shortly.
This is the test conductor. Report system status.
Support systems are go for static test.
Low-speed systems are go. High-speed systems are go.
Ultrasonic data systems are go.
TVC systems are go.
High-speed video systems are go. Motor temperatures are go.
We are go for BOLE DM1 static test.
This drone's about to get hot. I'd back off. How wide is the booster? 3.7 meter diameter. Yeah, look at that. Very interesting. So, guys, I noticed something, and I'm not sure if this is right or not, but so this is a 5-segment booster. So you have one segment from here back, then another, then another, then another,
T
and then
minus
another.
3 minutes.
So you have 1,
Low
2,
speed data
3,
operators
4,
begin recording.
5. Right?
High speed data operators at T minus 70 seconds begin recording and report at that time.
So these are carbon fiber or carbon composite casings, right? I think they actually said it was carbon fiber. So if somebody asked me if they're carbon fiber before, I thought they were composite. They're actually fiber. But it looks like the barrel segments are fiber. It looks like at the segment joining area where the booster clevis is and the O-rings, yes, those O-rings, they're still utilizing a steel component, which is very interesting. So that thing it's steel carbon, steel carbon, steel carbon between each segment. Which is very interesting to me. It's not an old shuttle booster. This is a new SLS booster. See? Look. So they have a carbon fiber barrel that is adjoining a steel bulkhead segment with a clevis with the O-rings together to another steel clevis
T minus
to carbon.
2 minutes.
T minus 2 minutes. We going or what? Yeah, oh yeah. The sucker's gonna go big, man. Won't the expansion rate difference cause issues? So, Ayayaran, I'm not 100% sure if that's what I'm looking at. It looks like steel and carbon, steel and carbon.
90 seconds.
That's an observation for me. I don't know. That's what it looks like, but I could be wrong. In which case, if I'm wrong,
80 seconds.
then it'll be
Test
fine.
control coordinator, stand by to commit the motor.
But if I saw what I saw, yeah, maybe.
T minus 70 seconds.
Commit the motor.
The motor is committed.
What's on the penalty end nozzle that's about to get cooked? That is a mirror.
T minus 60 seconds.
There's a camera over here that's looking
All
at
high-speed systems are recording.
Roger.
that's looking at the
Ultrasonic data
mirror,
system is recording.
so they
Roger.
can see the booster plug.
T minus 50 seconds.
The booster plug fly out.
EDC
I'll
is
show
go
you.
for static thrust.
Roger.
14 meganewtons coming out of this booster, guys.
T
That's
minus 40 seconds.
that's the equivalent of 6 Raptor engines. One SRB is as powerful as 6 Raptors, dude.
T minus 30 seconds.
Here we go.
T minus 20 seconds. T minus 15 seconds. T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Send it.
Fire.
Yo.
T plus 5 seconds. T plus 10 seconds.
That's nice.
T plus 20 seconds.
No audio. Okay.
T plus 30 seconds.
Look at it. The radiating heat is actually melting.
T plus 40
Sand.
seconds.
See all the smoke coming off? See that? It's melting everything around it, just the heat. That's why this camera
T
is so
plus
far away.
50 seconds.
It's turning the sand into glass.
T plus 60 seconds.
Should get another minute and a half here.
T plus 70 seconds.
Does NSF have sound?
Enabled.
Nope.
T plus 80 seconds.
Central support system operator, enable the deluge, CO2, and quench tool controls.
Enabled.
Look at it. It's just shredding and
T
melting
plus 90
everything around
seconds.
it.
Open the
is
accumulator
there's a
enable
lot of
valve.
heat coming off of this thing.
Accumulators enabled.
T plus 100 seconds.
Oh. Oh.
Activate aft deluge.
Oh.
Activated.
Whoa. T plus 100
Oh, that's
seconds.
bad. That's bad. That's not good. That's not good. That's not good. That's not good. That's really not good.
T plus 120 seconds.
Stop! Oh, that's not good. Oh, it's bad. Yeah, that's bad. The nozzle decided
Activate
to.
head end CO2.
The nozzle decided, and the booster skirt is gone. That's not. Oh.
Quench tool forward. Command forward. Activate aft CO2.
Yeah, you might want to call the fire department. Part of it is over there, and it's now causing a fire. Part of the nozzle got some pretty good distance. Part of it's up there on the hill, also causing a fire.
Roger. T plus 160 seconds.
Yeah, that's extreme loss in performance, extreme loss in efficiency.
T plus 170 seconds.
That
high-speed data operators.
That was a failure, guys. That failed. That was like ship 36 bad. That's not good. Dude, the nozzle is toast. Actually toast. The CO2 purging system is working though. It put the fire out. But you got a problem. The entire hillside is on fire at this point. Yeah, from where part of the nozzle landed over there, and over here, and over here, and over there. That's bad, guys. Oh, black screen. Nice.
High-speed data operators, stop recording.
That happened last time, Geek. Yeah, very interesting. That was actually worse. That was a worse failure. So it's very clear. Hey, where's Megan? Hey, Megan, where are you at? Come on back. Yeah, that. So, okay. This happened before when they did the Omega test. The thing is that nozzle was engineered. It's a hybrid nozzle for the SRB. What does that mean? So the nozzle uses an ablator. All right. The nozzle on an SRB for cooling purposes is made out of heat shield. Right. It ablates away. But the problem is that nozzle, when I say it's a hybrid nozzle, it is optimized for vacuum, right? Because that's where the booster is going to do the majority of its work, right? It's optimized for up there. If you test a vacuum optimized nozzle down here with the SRB, especially with these SRBs, which include a regressive thrust curve in them, and thus a regressive thrust curve, oh, there's the fire truck. Call the fire department. This one's out of control. If you have these boosters are designed with a receding thrust curve. Now I don't know for sure if these ones have that. Basically, over time the thrust goes down, right, to throttle back and for separation. You can't throttle them, right? So they actually pack the grain inside of the SRB in a way that makes the thrust go down. If your thrust is going down, your chamber pressure goes down. So the problem is when that happens on this thing with this nozzle that's vacuum optimized, you end up getting flow separation inside of the nozzle. That creates non-uniform heating inside of the nozzle, which causes it to fail. That's what happened during the Omega test. I have no reason to believe that that's not what happened here. Hey, part of the nozzle got some nice distance. Look at that. Some nice distance. Are they the same booster that will be used on Artemis 2? No, they are not. Let's... Oh. Yeah, that was not great. That's not supposed... I mean, unless they tested it with that instrumentation, knowing that it was going to do that. I mean, these Block 2 SLS boosters are not RSRBs. They are designed to be expended. So, guys, I'm not going to rule it out, but it might be entirely possible that that was on purpose. But judging by the in mission control, probably not. But also, here, I'll show you again.
Activated.
I saw it. I saw the, see the flame? All right, the flame distinctly changes shape here for a second. Like, and it starts.
Activate forward deluge.
Look, see
Activated.
that? See that little puff of smoke right there? I saw that and I was like, and right when I was about
Plus 120 seconds.
see, look at the flame. See it start to go up and see it start to puff out up here? I saw that and I was just about to say that flame doesn't look right. And then it popped. Watch.
Activate head end CO2.
This is a replay, guys.
Activated.
Activate quench tool forward, command forward.
They're
Activate
live?
AFC.
I have to say, it took me
Okay,
a minute.
hold on.
I had to recover. That was incredibly cool. So, here with me now to talk about the test and answer a few of your questions is NASA's Dave Reynolds, Program Manager of Booster Subsystems for the Space Launch System, and Northrop Grumman's Doug Hurley,
Dougie!
Senior Director of Strategy and Business Development.
Dougie Fresh!
Gentlemen, thank you for joining me, especially so quick after the test. That was fantastic. This first question is going to be for you. Obviously, we just witnessed something very cool, and that was the first time it had ever been fired up. Can you tell us a little bit about what we just
Yes, I
saw,
can.
and did you consider it? Was it exactly what you wanted it to be?
Sure. Yeah, thanks for having me on and having an opportunity to talk about something that I've been really excited about for a long time. So what we just watched was the most powerful man-rated rocket motor ever tested. It's absolutely amazing what we just watched. A rocket motor putting out almost 4 million pounds of thrust. You can see from the side of the mountain up there, it's still feeling the effects of that test. This test is a brand new booster from tip to tail. There are so many things that are different about this booster. It actually has very little relationship to the current boosters that are flying on the Artemis 2 mission that's coming up. And so we were expecting to learn a lot of things, and I guarantee that we're going to spend the next 6 months digging through all of that data and finding out what we need to do. Now, we push the margins on almost every material that we have, and that, I would suspect, is probably one of the first things that we are going to learn, is how close did we come to the edge of those margins. And if we did get too close to the edge that we're not comfortable, we've got other plans in place to move forward and build another motor that can teach us the things that we needed to learn from.
Why would you say that?
Fantastic, thank you. So, Doug, I was actually able to tour a little bit of the facility yesterday, saw a lot of amazing things.
Why would you say that?
One of our viewers is actually asking,
what
specifically does Northrop Grumman build and test here that's related for the Space Launch System?
Well, we've built solid rocket boosters
weird to bring that up.
here for even the shuttle since like the late 70s. So we've been building shuttle heritage, and then of course we transitioned to SLS several years ago, and we've repurposed 8 sets of shuttle boosters that are going to go on SLS. So it's an incredible facility, 20,000 acres. So we do a lot of solid rocket motor designing, testing, manufacturing out here, much more than just SLS.
Fantastic, thank you. So you mentioned a lot of the data that you're going to be studying. One viewer has actually asked, how do you monitor the test? Specifically in the chat, they're wondering about mirrors that are observed to observe the plume.
Yeah, so right behind the motor, right before you see it fire, there's actually a stand that has a mirror in it. Now, obviously, we want to understand how that flame front starts from the beginning of the motor and travels down. And there's no good way to put a camera that's going to survive that test. So what we do is have a giant mirror that sits behind the stand and point a camera at it so that we can see right up the bore of the motor. That tells us 2 things. First of all, we have a plug that allows us to, first of all, keep the bugs and the dirt out, but also to build up the pressure a little bit before it bursts. So that camera watches to see how that plug is going to break up.
Oh yeah,
But then when that thing breaks
it
up,
popped.
you can start to see the flame front
Worse
come
than
down.
Omega.
Now, the mirror
whole thing exploded.
doesn't last very long. Once again, pointing to the mountainside, we're going to find it probably tomorrow because it's probably halfway up the mountain. That's just what we expect every single time. But it is one way that we're able to characterize the flame front and how that plug breaks up.
Makes sense. All right, back to you talking about all that power, the propellant. One viewer is asking, what kind of fuel will be used?
So solid rocket motors are typically very similar. We use this ammonium perchlorate, which is a major constituent. We've got aluminum, we've got binders, we have oxidizers. So it's, and when it actually cures in the motor, it almost is like a pencil eraser type feel. I don't know, Dave. I mean, it's really interesting. It burns from the top down, and as we said, almost 4 million pounds of thrust out of this particular engine.
I felt that power. Yeah. It was more than I was expecting. I wasn't expecting that at all. It was incredible. All right, so one more question. You mentioned that there are a lot of different things between the current boosters for SLS and the ones we just witnessed. One of those is actually the color. Our current ones are obviously white. This one was black. Does that hold any significance?
So it does. The current boosters that we're flying with right now are mostly metallic. They were repurposed shuttle hardware, but we only have a limited supply of that. And so what we have learned over decades of building solid rocket motors is that a more efficient and faster and cheaper way to build rocket motors is through composite materials. What we used on this rocket was a carbon fiber filament that we wound around a mandrel, and that's why you see it being a different color. It's a dark color, but eventually we would probably end up painting it white because we want to control the temperature a little bit more, and white paint reflects the heat a little bit better. But on this one, we wanted to see exactly how the case behaved, and when you paint it, you cover up a little bit. And so because this is a development motor, and meaning we want to get as much data as we possibly can, that was one reason that we decided to leave it unpainted so that we can have better observation of the case. But composites are the modern way of building rocket motors, and we're advancing in that direction.
Okay, perfect. All right. Well, that looks like all the time that we actually have here. Any last thoughts? Everybody good? Wonderful.
It was an amazing test.
It was an amazing test. All right. Anything else from you?
No,
all right.
Just glad we had such a great team and crowd here to witness this first test, and it'd be great to see this thing fly sometime soon.
Absolutely. All right, great. What was the question from off the viewer? Special about the yes, SLS. Absolutely. All right, so these are very special to the SLS and for the Space Launch System rocket. We can't wait to see these fly. And we are so excited that you were able to join us here today. A big thank you to you. A big thank you to Julia and Alyssa for joining us as well. Thank you for tuning in. If you'd like to rewatch the test, be sure to head over to NASA's Marshall YouTube channel. Be sure to also follow our NASA Artemis accounts and Marshall social media accounts for all your SLS related news. And we can't wait to see you for the launch of Artemis 2, the first crewed mission to the moon in over 50 years. Enjoy, and we'll see you soon. Thank you.
So, guys, I'm gonna give you a little lesson here about body language. Do they look happy? Just kind of sit and look at this. Do those dudes look like they just conducted a successful test? Okay, I might be reading too much into this. It looks like they're at a funeral pyre. Yeah. Oh, I'm so sorry for your loss. Well, it was a pyre. Yeah, okay, that's fair. That's fair. So it might be, I might be reading too much into it. Yeah, like, once again, little lesson in body language there. They don't look too happy, and yeah, exactly, they're ignoring the fire. Yeah, the mountain behind them is actually on fire. Anyway, so the guy that runs the program over there said something very interesting to me. They didn't acknowledge that the thing just blew up on the test stand. But what the guy did say, what he did say was, well, if this test didn't go exactly, we got to comb through the data and we'll look through it. And if this test didn't go exactly how we wanted, well, we got another development booster that we could put up on the test stand and we'll fire that one instead. That's What an odd thing to say. Why would you say that? You ever see that Bart Simpson thing? What an odd thing to say. Like, why would you bring that up? Did it not go well? why would you bring that up? 6 months to figure out what happened. I'll tell you what happened. It popped. Can we see it again? Sure. Yeah, here. Oh, we'll back it up. Let me scrub through. Like I said, I saw the flames starting to do something that was not great. Here, let's see. Right around here.
80 seconds.
Central Support System Operator, enable the deluge, CO2, and quench tool control.
All right, so let's watch this. Let's watch this in slow. Actually, we'll just do a fast motion play.
Enabled.
T plus 90 seconds.
Open the accumulator
Can't
enable
see
valve.
me. You might be right. The bottom of the nozzle is
Accumulator's
definitely
enabled.
having some burn through. I just saw it.
T plus 100 seconds.
Activate aft deluge.
Activated.
Whoa. T plus 110 seconds.
Activate forward deluge.
Activated.
T plus 120 seconds.
Let's just see that in an instant replay. Yeah, they're moving it around, but I noticed something. Look. Can't see me over in the YouTube chat. You suggested that could it be the heat that's getting trapped there. There's definitely nozzle burn through happening right there. See it? See the burn marks? See the charring? That's bad. That's very bad. It doesn't matter the rocket engine. That's extremely bad. That's the reason, like, for instance, why most of the rocket providers that we watch, like we watched Electron a little bit earlier, and we watched two Falcon 9 launches over the last 2 days, right? All their second stage cameras are looking at the nozzle. They're looking for that right there. See that? That's burn through. I might be looking at this incorrectly. That's burn through. That might be because it's close to the ground. But it seems like the point of failure is coming from somewhere else. Would this be classified as an overpressure event? No. Nozzle burn through. It could be heat reflecting off the ground. That could be normal. I don't think that that's what caused that failure, but I need to see this in kind of slow motion here. Because the entire aft segment, which is purged usually, you notice there's blankets right here. There's a blanket around that's hugging the nozzle. This area is usually purged out with nitrogen. So there's non-reactive stuff going on there in case something goes spicy. Or at least it was on the shuttle. I don't know what it is now. That one, I don't see. Oh, yep. See, burn through on the top of the nozzle. Guys, that's bad. That's really bad because that's not coming from the nozzle. If you look. What are you doing, YouTube? Oh, wait. The initial thing didn't come from the nozzle. That came out of the aft segment. It came out of the booster skirt, which is bad. See, look, you could see the booster skirt right there. It pressurizes for a second. The skirt starts to go out, and then it fails completely. If it's coming proverbially upstream in front of that skirt, that means it's the throat. Not good. Because that's how this nozzle works, guys. The aft end of the SRB segment basically tapers out, right? And the nozzle for this is basically hugging the outside of that, and it can turn. The very end of the aft SRB segment is kind of like a ball joint almost, and the nozzle kind of picks up on it, and it can move. They can move the nozzle around with thrust vector control. Because this is happening north, proverbially upstream from the booster skirt, that means it's coming from the throat or the not like where the nozzle extension picks up, which is not great. That is not the same failure that happened to Omega. Look, that is straight burn through. But what's going on here is it's burn through that's happening somewhere up around the throat of this nozzle, and it's going out, and the booster aft skirt is deflecting it backwards. What's an Omega? That was a Northrop Grumman rocket that they canceled. They tested an Omega booster on this pad, and it exploded. Wait. They are doing thrust vector control. That's a thrust vector control liner. What are you talking about? Oh yeah. See, all this smoke right here is that skirt, the blankets right there. That's all of it burning off. See, some of it came off right there. And then the nozzle is being burned from the outside and the inside. The flame should be coming from here, not from over here, because the nozzle burned from the outside and the inside. You see a complete failure of the nozzle right there. Now, couple of telling things. Look over there. See that little guy? I would worry about that little guy. That means, look, the throat was gonna, the throat and the where it picks up on the nozzle, it failed over there too. It was gonna fail over there. It took complete failure of the nozzle to blow it out, but hey, stop it, YouTube. Yep, complete failure. That is a complete failure of the entire nozzle and aft skirt assembly. That's not good. That's really bad. Now, the good news, and see, here's the other thing. The reason I know that it's the throat of the nozzle and not like where the nozzle extension picks up on the throat of the SRB is because, look, after the failure, you have SRB exhaust coming out of the booster skirt. The booster skirt is acting as your nozzle. If the throat of the SRB is right here, it's inside of the skirt. Let me get you a diagram. I'll show you. I've looked at these a lot. I know how they're put together. Give me one moment. Here we go. This will work. So look. Check this out, dudes. Now, keep in mind, this is a shuttle SRB. This is what's called an RSRB, reusable solid rocket booster. The BOLE boosters, I refuse to call them BOLE. That just sounds strange, are called something different. Now, look. See, they have a nozzle extension, okay? The aft segment has the bottom, and it has the throat right there. And then you have the throat, and you start to have the nozzle. You start to have the nozzle, and then you have the extension. The extension is ablative. This piece is ablative. This is the part that is outside of the booster aft skirt, right here. And you have the heat blankets right there that are nitrogen purged. Okay. What is, Baron, you linked Space Engineer? What does he say? The nozzle is completely gone. Everything is completely gone, and I'll tell you why. Guys, I'm basically coming up with the hypothesis for a failure right here. Look. Right? See where that black ring is? That's where it failed. I'm pretty damn sure. The reason why is because, look, that, first of all, the throat right around the black ring, because at the end of the day, this is still a De Laval nozzle. It's a convergent divergent design. That is the hottest part. It is the hottest part of the entire SRB, right there, where the gas gets compressed through the throat. PV equals nRT. You take hot gas, you compress it even further, it's going to get even hotter. Pretty straightforward stuff, right? The throat is north of the back of the aft skirt. And you saw these heat blankets right here inflate. They inflated, and then it popped. The nozzle extension, right, and the nozzle liner piece right here, the liner piece is north of that skirt. But like when I say north, I mean that way. It's upstream, you know, because the rocket flows gas this way. So upstream of that skirt. But the skirt is attached right at the extension piece. See this flange right here? That's where that skirt is attached. We didn't see a failure come from that. We saw a failure come from inside of the skirt at the throat. The throat failed. I'm pretty damn sure. Did they redesign the throat? Well, the program manager, Hellfish, said that it was most of this is redesigned from the SRBs. So could the thrust vector control have caused damage to the nozzle extension? Well, supposedly these boosters have an electronic thrust vector control system. It could be that something failed with that. But once again, where the failure came from, it's possible. I would say it's possible because there are two thrust vector controllers. There's one at the top of the booster and there's one on the side. You only need two. This one for moving the nozzle this way and this one for moving the nozzle that way for pitch and yaw, right? The failure point did come from where the x-axis thrust vector controller is clocked. It definitely came from the very, very top. See? But see how it inflates? See how it inflated the blankets? It inflated the heat blankets, pressurizing the aft skirt and then blowing it out immediately. Throat all day. It could be the liner. It could be thrust vector control. But here's the thing. By the time you see full nozzle failure, look at that. Look at the way that gas is coming out. That gas is pushing up against the booster aft skirt and then pushing that way. If it was the liner, we wouldn't see it go kind of up and out. It would just go that way. Does that make sense? It would just keep going with the direction of flames. This is a hole. That's a hole in the throat. Throat all day, every day, bro. No. And then because the nozzle is being heated on the outside and the in, it's ablating in both sides, and you see a full nozzle failure here in a moment. You'll see it fail completely. There was the failure. Right there. See the parts of the nozzle are flying around? I know, subtle. But now look. The other reason why I know it's throat. Well, keep in mind the nozzle liner and extension failing could have pulled the throat with it, right? It could have pulled it with. But look at the way that the flames are propagating out of the booster aft skirt. The booster aft skirt is acting as your nozzle. So let's go back to this picture. If the booster aft skirt is acting as the nozzle, that means this part is gone too. Because if that was the case, if it failed like right here, right? If it failed right there or right there, you wouldn't see the flames completely filling up the aft skirt. You wouldn't see that. The flames are coming out of the aft skirt like it's a nozzle. That only happens when you lose the entire aft segment. So you know what, dudes? Now that I'm really thinking about this, I don't think, you know what? I changed my mind. I don't think the throat failed. I think the whole aft segment failed. Because look at the way the flames are coming out of this thing. Flames are coming out like the SRB, there's nothing here. Like the gases are just flowing out and going out the sides. Especially up at the top. And judging by the amount of FOD that came out of this thing, I think the aft segment failed completely. That's crazy, dude. In fact, it absolutely failed. It failed completely. And what sucks is that it fried that whatever thrust vector control systems were in there. Those probably got shot out too. And you're seeing burn through on the aft skirt, which is, that's bad. It looks like they had, my guess, rarest would be, oh, yep. See that right there? Whatever that is, see that bright thing that comes out? Whatever that is a piece of the SRB that detached. See that? Yeah, it's over there somewhere. Oh, yep, there it is. You see pieces of it up there. See it? See it flying away? Dude, you can see pieces of it. Look. Look. Watch. Watch what comes out of the fireball. Right there. Oh, yeah. Oh, yeah, that nozzle's gone. The whole aft segment is destroyed. That's really bad. Yeah, that's really bad. That's not SRB fuel. If it was solid rocket fuel, Hellfish, it would be on fire. That's not on fire. That piece got ejected in a ball of fire. Dude, like, once again, I don't mean to doom and gloom. I'm thinking this whole part is gone. And it could have been from a throat failure. You're not likely to see that from a liner failure right here. So the liner is where the ablator nozzle connects to it. And there's a little bit of a liner piece that allows the nozzle to move over the fixed throat with the thrust vector control. Right? But, yeah, judging by how the flames were coming out of the aft skirt, I'm going to go ahead and say it's probably gone from about here back. That's... Does Artemis depend on the thrust vector control of the SRB? Yeah. IMO, in your opinion, you have no data. Keep in mind, I have no data either. They're gonna have to comb through it. And they're gonna have to figure it out. But that looks like throat burn through and complete aft segment failure. I've encountered that pattern of damage during a couple tests years ago. BOLE is using electric thrust vector control, and excessive vibration loads or improper load transfer will destroy it. And on the other side, they were also doing thrust vector control tests that could nozzle collapse from side loads. Adding a new thrust vector control system could also alter exhaust flow dynamics, causing uneven heat distribution and pressure spikes. Yeah, Baron, I was more talking about what happened. In terms of what caused it, I don't know. I know that the throat failed, though, but yeah, that's a good point. There's a bunch of things that could have caused that. I know, I'm observing what happened here. But yeah, possible. SRBs might seem simple, but they're not. It's a complicated thing. You're controlling a gigantic explosion. I think it was throat failure due to erosion caused by too much pressure. If I recall correctly, there's a point where too much pressure increases erosion but won't pop the SRB. Possible. Pick from a couple of days ago without the aft skirt. Yeah, see all up in here? Okay, so here's your extension. This piece right here, that's the liner piece right there, that white stripe. And then you have the throat down there. Like I said, dudes, we saw flames coming out over here. After something popped completely, we saw the flames come out in the aft segment was being used as the aft skirt was being used as the nozzle. Which means that, see where all those bolts are down there? That means that failed completely. The reason why is because if you see this white part right there, if the throat and the aft chamber didn't, in the aft segment didn't, if it was just the throat that failed, all right, you would have seen the flames shoot out in like a straight line, but we didn't. We saw, because if this piece was still there, the flames would have shot out and gone this way and then up, right? But we didn't see that. We saw flames, we saw the aft nozzle segment being used as your nozzle, or the aft skirt being used as a nozzle, which means it failed up here. See where these triangles are? That means this whole, basically from where those triangles are, back is gone. It's gone. And we saw it shoot out the side. And for what it's worth, that definitely is electric thrust vector control. That's ETVC right there. Actually, look, they have the booster clocked 45 degrees from where I thought. So the x-axis thrust vector controller is actually at like the 2 o'clock position. And the y-axis thrust vector controller is at like the 4 o'clock position. The failure came from over there. It came from the very top of the booster. So it failed up here somewhere. So I'm going to rule out thrust vector controller. Is one of those things labeled inert? Possibly, Tessa. I doubt that thing got out of there unscathed. That's a billet aluminum aft skirt. Guys, look at the ortho grid. It's billet. It's a billet aluminum aft skirt. Why would you? Okay. And it's bolted together. See the bolt on the flange? That's the flange point between the two segments, and it's bolted together. Why? Okay. Why billet? You know, Aaron, I'm not sure. Hey, remember when we said different expansion rates a second ago and how they could cause problems if you're using differential materials? Remember you mentioned that? Yeah. You remember that. That was fun. That was funny. This has been a cursed year for spaceflight. No, I mean FYI, I don't think so, dude. I think that, and also look at the trash can if you want scale here. This is a gigantic freaking booster. It's very, very big. I don't think so, dudes. What I do think is going on here is that the space program is changing. Everything's changing. That's why we see failures. Everything is changing, not because of like enshittification or anything, or entropy. The industry is changing, and the industry is trying new things. Carbon casing boosters, right? Stainless steel pressure vessels. You know, where the industry is changing, and they're trying. You see new things. You're trying new things with rocket science instead of just doing what you've been doing for the last 50 years. Explosions are going to happen. I don't think this is a mark towards Northrop Grumman. I think they should put another one on a test stand, dude. But the thing is that Northrop Grumman doesn't seem to be too incredibly hardware rich in their program. The program manager, I forget his name. I think his name was John. He said that they're going to go through the data on this for 6 months and then maybe test another one. That's not hardware rich. But if you're trying something as new as this, there's a reason why you probably want to do some hardware rich testing, especially when you're trying a bunch of new things all at once. Did it pop again? Here, Panta, let me show you.
T plus 60 seconds.
Oh.
Enable the delete.
Accumulators enabled.
Watch. It's a very subtle failure. I'll show you.
T plus 100 seconds.
Watch. Oh. You see that little guy?
Activate aft deluge.
That's bad.
Activated.
That's also bad.
Whoa.
T plus 110 seconds.
Oh. Yep. There's the yeah. Oh wow.
Activate forward deluge.
Man, watching that in real time, dude. It didn't take long for that aft segment to yeet out the back of the vehicle. Holy crap. So check this out. Look,
T plus 100 seconds.
throat failure right there.
Activate aft deluge.
Total nozzle
Activated.
failure right there.
Whoa. T
And
plus
then
110
boom, aft
seconds.
segment gets shot out.
Activate forward deluge.
That's bad. That's really bad.
Activated.
Yeah. Oh. It exploded when they started the deluge. Could that have factored in? The deluge system on this Dean is not what you think it is. It's not like a water suppression system. To my knowledge, this little lever arm thingamajigger here, that's the deluge system. There's basically a gas nozzle here, right? And when the booster flame out happens, they turn this thing in there to extinguish the fire. That's what we've seen in the past. And I think it did do it, but I think they cut the camera.
T plus 100 seconds.
Activate aft deluge.
Activated.
Whoa. T plus 110 seconds.
Activate forward deluge.
Activated.
Man, that thing got some distance.
Activated.
Whoa. T plus.
Listen. When this second explosion happens and you see the nozzle shoot out and you see part of it, or not nozzle, you see part of the aft segment shoot apart and go up here somewhere, you hear the lady go, watch, listen.
110 seconds.
Activate forward deluge.
Activated.
T plus 120 seconds.
So right now, because you have a loss of chamber pressure, it's basically just shooting fire out the back. It's a nice flamethrower. See how the flames aren't going like all the way up the hill? It's an extreme loss of efficiency because your flow rate...
Activate head end CO2.
Astro 95,
Activated.
Real-time reaction was priceless.
Activate
Keep up the solid work.
Quench tool forward, command forward.
Dude, she can't
Activate
even talk straight. Astro 95, $10 super chat. Keep up the solid work. Thanks, man. And keep in mind, this is all speculative on my part. I'm probably wrong, but that's definitely what it looked like. Right after the third pop, you could see some green in the middle of the cloud. Yeah. See, this is why at this point, dudes, the guy is still talking. He's like, oh, T plus this second, T plus 6 second, because the booster should still be lit. It should fly for 2 minutes 30 seconds on a booster burn like this. So it should it's 120. So 150 seconds should have been flame out, if I'm understanding that right.
T plus 100 seconds.
Activate aft deluge.
Activated.
Whoa. T plus 110 seconds.
Activate forward deluge.
Activated.
T plus 120 seconds.
Maybe the deluge system is not the that thing, guys. I'm not sure. Joe Barnard 1, NASA 0, in your face!
Activate head end CO2.
Activated.
Activate quench tool forward, command forward. Activate aft CO2.
Yeah, you can see over there, there's parts of the nozzle over here and over here and over here that are now causing a gigantic fire.
Activated.
Yeah, part of it landed over there. So, see, there's the swing arm.
TVC power is disabled.
That swing arm.
Roger.
Oh, the TVC power is disabled. Oh, that's good.
T plus 160.
Hey, hold on, what did she say?
TVC power is disabled.
Roger. T plus 160 seconds. T plus 170 seconds. High-speed data operators. Stand by.
Interesting, FYI. See, there's your CO2 suppressor. There's not much to suppress out, believe me. All the flames came out. It let out all the freedom a little too fast. Yeah, I don't need to worry about the thrust vector controller. It's probably up the hill. Probably like a mile up the hill. You don't need to worry about shutting it off. It disconnected itself. The carbon fiber segments worked. Except for the aft segment. The aft segment, in fact, did not work. Started pretty good brush fire. Yeah, because some of the aft segments over there, some of the nozzles over there, and over there, and over there, and over there. Yeah. Yeah. You know what I'm kind of curious, guys, about? Here, let me go over here. Great success. I am now very curious about when the Omega nozzle failed. When did that pop? So this is, yeah, all right. Let's see.
5, 4, 3.
Here, let me get my timer out just in case they're not calling it. All right, ready?
2, 1, fire.
We have ignition of Omega's first stage,
T
a
plus
major
5
milestone
seconds.
supporting the future of national security space
T plus 10 seconds.
for the U.S. Air Force.
It is a new design.
20 seconds.
Joe, it's a carbon fiber SRB instead of steel like the space shuttles.
T plus 30 seconds.
All right, so the BOLE booster failed at like 100 seconds and change.
T plus 40 seconds.
Same test stand for what it's worth.
T plus 50 seconds. T plus 60 seconds.
This test wasn't serious. The one that went today, yeah, absolutely.
T plus 80 seconds. T plus 90 seconds. T plus 100 seconds.
So that's where the BOLE booster failed.
Enabled. T plus 110 seconds.
Open the accumulator enable valve.
Accumulator is enabled. T plus 120 seconds.
So, guys, the other reason why I knew that the entire aft segment came off is because, well, fortunately for us, with Omega, they had the nozzle. The nozzle had problems. So the nozzle exploded. And when the nozzle exploded, it blew the aft skirt off completely. Or actually, no, that one didn't have an aft skirt. So we know that this was a nozzle failure. It was the nozzle. You could see it. And how the flames are coming out after the nozzle fails and not the throat, right? How that's happening? It's shooting it out in basically a column. Like, watch after it fails.
T plus 120.
See how the flames are coming out of there? Now, if the booster skirt was there, the booster skirt would be up here where my mouse cursor was somewhere. So if the throat didn't fail, you would have seen that coming out of the back of that booster. That's not what we saw. We saw flames coming out basically using the aft skirt as the nozzle. Watch.
Activated.
No, hey, come back.
T plus 110 seconds.
Yeah, see that light, that piece that just came out of there? That is this piece in there. It's this entire piece the entire back part where it starts to curve down, shooting out. Because if the throat failed or the nozzle liner failed, right, you would see a concentrated flame coming out like that. It would kind of be, you know, coming out like this, but we didn't. We saw it expand sideways. That sideways expansion is an entire aft segment delamination, I guess would be the right way to say that.
Activate aft deluge.
Activated.
Whoa. T plus 110 seconds.
There goes your
Activate forward deluge.
Activated.
T plus 120 seconds.
So when they go to the next shot, look at how the flames are coming out. They don't really burn from top to bottom. Not an SRB like this. They burn outwards. That's how they control. That's how they control the
Activate
throttle.
head and CO2.
With combustion chamber variable geometry, because
Activated.
your combustion chamber burns because it's solid rocket fuel.
Activate quench tool forward command forward. Activate aft CO2.
Activated.
So see right there. Back it up a little bit. See how the aft skirt is working as your nozzle? Dude, the entire aft segment failed. That's bad. You were asleep? What did you miss? All right, Andrew, we'll take a look. This was the BOLE 5-segment booster test. It's going pretty good. It's going pretty good, up until about 100 seconds.
T plus 100 seconds.
Yeah, see that? See that little
Activate
guy?
aft deluge.
Yeah, that.
Activated.
Yeah, that's bad.
Whoa. T plus 110 seconds.
Activate forward deluge.
Activated.
T plus 120 seconds.
So my running hypothesis now is that the entire back from basically see where that tape is? The inside of that. So all right, let's zoom in a little ways. Okay, so you see where the throat bolts into the aft segment right there, and see all those bolts right there? And then see you have the concave part of the aft segment, and then you see where these billet, the aluminum stringer is right here, where these triangles are. Everything from here back failed, is gone. It's up the mountain somewhere. That's my running hypothesis. The entire aft segment failed completely. But the entire aft segment failed after, looks like they got burned through up here, right where my mouse cursor is. It looks like they got a burn through right in this area here, or somewhere right there at the throat, which is the hottest part. Non-uniform heating inside of the nozzle or throat. It blew out the aft booster. It blew out, well, basically blew this out, blew the nozzle out, and then blew the aft segment completely out. That's what those big explosions were. Now, what caused that? I don't know. I have no idea. I don't have the data in front of me. I wouldn't be able to tell you. What I can tell you is that part of the SRB is up the mountain, and it really shouldn't be. Wasn't Northrop Grumman supposed to make solids for new ICBMs? Well, their solid fuel clearly works really well. Yeah, Baron. Yeah. Looks like it failed at almost the same time for the ultimate failure. Well, the Omega rocket failed at about 154 seconds, believe it or not, which would be closer to 120 seconds, right? 118 seconds versus 102. And it looks like the nozzle failed, Tessa, on Omega. I'm telling you, the throat failed here. You see the difference? It wasn't the exact same explosion, right? It wasn't the same thing. We saw a completely different bit of behavior here, which tells me that it's throat and not nozzle, because that nozzle looks very similar. Could be different, though. I don't know. From Northrop Contact, failure was at the nozzle throat. From the Northrop Contact, Vulcan, failure was at the nozzle throat casings. Failure was at the nozzle. Throat casings don't show any issues. Initial belief is that erosion modeling from subscale testing didn't scale as expected. and they had been very aggressive with the nozzle build on this motor. Don't seem too bothered. Yeah, they got another one. Put another one on the test stand. Send it. Failures at the nozzle. Throat casing. I don't know, man. It could be the liner. So if it's not throat or anything, if it's not throat, the aft segment of these style of SRBs. So see how there's a highlighted segment piece right here? That's the nozzle extension. The nozzle extension is where this thing has thrust vector control. The throat and the small part of the nozzle right here, so that it converges, right? And then it starts to diverge, and then you have a liner, and the liner is attached to your nozzle. There's a seal right there. Could have been that failed too. Ultimately, they're going to have to go up the mountain, Vulcan, to figure out where the aft segment is because, dude, I'm pretty sure, keep in mind this is a cascading failure. I'm pretty sure that, like, from about here back is, like, up the hill a little ways and probably on fire. Yeah, maybe, Tessa, yeah. If it had failed there, the entire aft skirt would have come off. Yeah. Yeah, I'm not sure. I disagree, my friend. So check this out, dude. Want to see something interesting? So Vulcan, what's tipping me off for this, all right? So take a look.
10 seconds.
Nope. What's tipping me off for this is like right around 100 seconds, dude.
Ooh.
So
plus 100 seconds.
Watch. You had your initial failure right there. Now that could have been the liner, could have been the extension, but so right there, that's telling me either the liner. Well, actually, I suppose you're probably right with initial failure because I'm talking about what happens after this, which I don't know if that counts for good data or whatever. No, it doesn't. Like, that's not your initial point of failure. So either the throat or the liner popped, and from what you're saying, it's not throat, but yeah, okay, I'm seeing it. So guys, see how the flames aren't completely coming out the booster aft skirt? See how the flames are this way? That kind of lines up with Omega, with what Omega's doing right there. So yeah, could be wrong. I could be wrong. That's fine. I know I'm not wrong after what happens after that though.
Activated.
Like after that, see the booster aft. See Vulcan, check this out. The booster aft skirt is being used as a nozzle, so that tells me that the entire back of that is not existent anymore. Part of it is right there, and maybe right there, and this little piece right here. Here. See what I'm saying? I was saying it was the throat. I missed a comma in my first sentence. Oh. Yeah. So, well, they're going to have to find some pieces of it because the pieces of the throat are over there. So, dude, you might, yeah, well, Vulcan, that's interesting because that's what I was saying before. That's a failure at the throat. It's not at the extension. Because of the way the flames, it's, okay, cool. So okay, all right, I read your sentence wrong. I was like, maybe, I don't know, dude. So back this up. What tipped me off to it is this shot right there. Look where that flame comes out. And more importantly, look where the direction of that flame is going, okay? So peep this, dude. BOLE is built a fair bit differently than the RSRBs. Yeah. Let me see if I can find you a diagram. Yeah, I would love to see a BOLE comparison because I've been using the RSRBs. So check this out. Look at how this thing pops, dude. So something fails right there, and then you clearly have a jet here that's pointed up, right? You have a jet that's going this way. Now, I know what you're saying. Like, well, EJ, the flames are going that way. Well, the flames are going up. They're going up. They're hitting the booster skirt, this kind of conic segment at the very back, and then they're going out. Because if there was a failure and the flames were going that way anyway, they would just get caught up with the plume. This is a radial nozzle, a radial throat burn through, which means like if the flames are going that way, those flames are going this way. That's not good. What do I always say about rockets? If you're exploding in more than one direction, you got a big problem.
Activate aft deluge.
And then right there is where the thing fails completely. Yeah. Yeah. So I'm going to go ahead and say that that's probably where the entire aft segment gave up. I'm going to retool stuff around a little bit. And then the pieces that the ejecta that you see that happens after that is most likely anything that was inside of that booster skirt. So like that part, that ratchet strap, whatever these pipes are. Wait, was this today? Yeah, BOLE had a little bit of an oopsie doopsie. Here, but I'll show you. It's very subtle. I noticed that it failed after gimbal test both times.
T plus 100 seconds.
Oh.
Activate aft deluge.
Activated.
Whoa. T plus 110 seconds.
Yeah, you can see part of it fly out over there. It got some good distance, dude.
Activated.
T plus 120 seconds.
SRBs don't backfire, dude. Your flames are going in one direction. The non-uniform heating, Tessa, I'm not even going to speculate as to why that happened, dude.
Activate head end.
That's frankly out of my wheelhouse, man. I don't know. That's why I want Vulcan to... I have good photos to show what bit failed. Let me send it to you on Discord. All right. That's why I'd be curious to see a diagram of the BOLE booster, because then I might be able to tell you what's different. I don't even know what caused this thing. I know that it's non-uniform heating. There's a lot of things, and this is where I run out of talent, so to speak. There's a bajillion things that could cause that. Without the data in front of me, I have no idea. How? It's an SRB. What is this, 1997? What do you mean? Also, man, I'm really happy that I took a break from working in the shop. If we were covering this in the shop, we'd be having a weird time right now. Oh, look, the part that is now up the mountain. Let me see. Let me check this stuff, Vulcan. I can't believe they let you take pictures of this stuff. Let's see what we got. Yeah, so see that blue part? That blue part's non-existent. Yeah, that blue part is gone. It's up the hill. The blue part is the part that's still attached. You sure about that? You sure about that? This is a solid rocket booster. Vulcan, okay, idiot question time. Are these steel? Are there clevises? Are they still using steel clevises? So it's a carbon mandrel winding with a metal clevis? Impressive that it didn't explode more than it did. When I see a failure, I see something slightly wrong, which isn't. It just scares me for no reason. Oh, no, this is cool, man. This is fun. I enjoy this. And I'm not enjoying it to dump on Northrop Grumman, dude. Like, I'm enjoying it because this is awesome. Like, figuring this out is super cool. And they will figure it out. I ain't worried about that. They're Northrop freaking Grumman. They're going to figure it out. You see those things that they used the other day? There was 6 of them that went in one direction and 9 of them that went in another direction. I ain't worried. It's just cool to try and figure out what went wrong. You know? It uses a metal clevis. And no one got hurt. Bingo. That's the big one. Fail on a test stand all you want, dude. I'm totally cool with that. Blow it up. Blow it up 1,000 times. I'm fine with it. Yeah, they're using a metal clevis. Interesting. Damn, dude, that's impressive. And the B-21 Raider is, yeah, a better version of that. The TVC being only on the nozzle extension is weird, right? It's not weird at all, May. The Space Shuttle has been doing that for 30 plus years. Yeah. Morton Thiokol invented that. Pretty awesome. In the second photo of the three you sent, wait a minute. These all say Futuramic. Did Futuramic make these? Make these parts? I know Futuramic. That's pretty cool. In the second photo, in the three I sent, that's the bit that failed and came out. Yeah, that part? Yeah, okay. Like I said, guys, I don't think it's a knock or anything towards Northrop Grumman. It's just this stuff takes time to get right. That's all. We're trying new things. That's pretty cool that they're using steel clevis. So, okay. Anybody that knows anything about space flight knows about the Challenger disaster, okay? Challenger disaster had to do with O-rings in the segmented SRBs. So the SRBs for SLS, the space shuttle, are made out of segments, right? The reason why is because that right there is one piece. Moving that around, yeah, well, solid rocket fuel, let's just say it's very dense, like me. Moving that around in one piece would be ridiculous. Nothing could move that. Only a crawler transporter could move one of those things. So they move them in segments because these segments are insanely heavy, right? Challenger disaster, when Challenger happened, there were O-rings, okay? Those, everybody knows about the O-rings between the segments. Yes, those O-rings, okay? That is, so the O-rings are in what's called an attachment clevis on the SRB. So basically part of the SRB, like what you see right there, see there's a channel in there? It's shaped like this if you looked at it on the side. The top of a segment is shaped like this. The bottom of the segment is shaped, actually nowadays it's shaped like that. And the clevi pick up on each other like this. The O-rings are in between where the two clevis attach, okay? It's very interesting to me that Northrop Grumman, well, go with what you know. That's actually super cool. They're going with a steel clevis. A steel clevis, and if I'm looking at this correctly, it has the rim on the inside there. See this beveled piece on the inside at the bottom of the clevis? That's a 3 O-ring design. So that's using post-Challenger SRB design. So it's a 3 O-ring clevis that's made out of steel. Because go with what you know. They tried doing that differently in the 80s and it didn't work. Well, it did work, except if you launched it in the cold. Anyway, what I'm trying to tell you is that Northrop Grumman did some pretty damn cool material engineering here because they have steel. They're using the steel clevis with the 3 O-ring design. Go with what you know. And that is actually mated to carbon fiber booster, carbon fiber barrels, which is, dude, that's actually pretty cool. It's not cool that part of it's up the hill on the test stand, but hey, wait, whatever. Up the hill at the test stand, but it's fine. Yeah, dude, look at that. I never noticed until I saw this test, dude. Look at that. Oh, that's trick, dude. How did they get the metal to adhere to that? How did they get the metal to adhere to the carbon fiber? That's cool, man. That's cool. Dude, that's some really trick material science. Hypothetically, what would have happened if it failed on an actual flight? Methane, that would have triggered an abort of Orion's launch abort system. Absolutely. Yeah, that would have absolutely triggered an abort. But that's why you test, baby. That's why you test. I've got PTSD from Titan. Keep in mind, fellas, this is an outward pushing pressure, not inward pushing pressure. Carbon fiber is very, very good at tensile. It's very good at tensile forces. It's not good at compression forces. They figured that one out the hard way. Oh, this is basically what the motor looks like at the moment. Yeah. Oh, nice, Vulcan. You got a picture of exactly what I'm talking about. Dude, I think that, see this piece right here? I think that piece failed too. That's just my hypothesis, though. I think this thing failed. You see where the extension bolts right here? I think it's that piece. I don't know if that's the same piece. I would say anything. Okay, so here's the aft segment, the aft steel segment right here. I'd say anything south of this is probably gone. And from what I can tell, dude, from how the flames are propagating, it's just how the flames are propagating. You tell me. This is probably burned through a little bit, probably charred here. Because that's the aft dome, is it not? Right here? Or no, the aft dome's over there. Yeah, okay. All right. No, I'm getting my pieces confused. We're talking about the same thing, dude. Yeah, I'm sorry. That was me. That part is gone. That part's non-existent. This part is okay. I'm still going to say that it's probably a little cooked, but it's all right. Yeah, I'm one step down from where I should have been. That one. So the blue part. I don't know, man. Vulcan, I'm not saying your friend's wrong. I'm probably wrong, but I'm gonna go ahead and say that part of that aft segment is probably not there. Part of it, not all of it, but part of it's probably not there. Hey, FYI, I got Twitch now. Oh, okay. Cool. I don't think it fully came off because of the skirt, right? The skirt is attached to this flat part of the blue segment, but I'm going to say that part of it probably went a little bit. Because if the throat failed, it's going to shoot hot gas out this way and probably melted some of that from the inside out. I'm just saying that based off what I saw with the flames, dude. That's not like my crazy hypothesis that I'm never going to let go of, right? Like, just after point of failure, dude, watch. We'll just take a look. So right there, throat, right? Right there, complete nozzle failure, right? And dude, Vulcan, just look at what I'm saying. Look at how those flames are coming out there, dude. Now keep in mind, this is in atmosphere. We're not at sea level, right? So you're going to get a little more expansion than usual, right? Because Utah's up in the mountains, right? But look at how the flames are propagating out of the nozzle, or the SRB skirt is acting as your nozzle now. So if part of that aft segment, if the aft segment was still here, well, like the aft segment would go down here like this, right? If that was the case, the flames would be coming out over here and going up, similar to Omega, like that. Dude, I'm not trying to be a dick. I think part of this is gone. Not the entire thing. We didn't lose the whole thing. I thought that they lost the whole thing, but you're right. See those bolts those bolts right there are where the skirt goes to it. So yeah, obviously you didn't lose all of it. I'm gonna say this is probably from maybe like here back is kaput. Omega had no skirt. No, I know. I understand that. And its aft dome did not fail. Without the converging nozzle, the pressure really drops, so that adds to the expansion. Yeah, that's what I'm trying to say. I'm thinking part of this got cooked, dude, because if it didn't, it would have looked like that. And I understand we didn't see any aft skirt, but look at Look at that. If that part was there, it would be converging and it would be down here somewhere, right? But we're not seeing that. We saw flames come out the booster skirt. Like flames are up here. I don't think that, I mean, don't get me wrong, you lost the throat, so you're not going to have a good day anyway, but I don't think the gas would come out of this dome segment and then go immediately up like that. They would shoot out and up. You know what I'm saying? Chris Titus Tech, thanks for the raid, man. We got a raid. Welcome in, Raiders. Testan is 4,300 feet above sea level. Thanks. How does the thrust vector control move the nozzle? So these types of SRBs use a these types of SRBs have a liner and an extension. The extension moves on it's this piece right here. That piece kind of is a ball and socket over the end of the nozzle almost, and the thrust vector control is attached to that. So what's going on, Raiders? Chris Titus Tech, what's going on, guys? We were just watching the so Northrop Grumman and NASA were testing their next generation rocket booster here for Artemis missions. Here, I'll show you guys what happened. I don't think it went right. Just watch. Right around 100 seconds, maybe something failed.
T plus 90 seconds.
Open the accumulator enable valve.
So just keep
accumulator
this.
is enabled.
T
So watch
plus
up the top.
100 seconds.
Yep, see that? Yeah, that's not great. That's really not
Activated.
great. Yeah,
Whoa.
that's bad.
T plus 110 seconds.
I'm just going out on a limb there.
Activated.
T plus 120 seconds.
Anyway, guys, I don't think I know Chris Titus Tech. What does Chris do? What games does Chris play? If at all. I mean, you could be on Twitch and not play games at all anymore. Hey, Chris. Mostly Linux content. All right, right on. Cool, man. I like rockets and cars and video games. I do all three of them on this Twitch channel. Right now, we're doing rockets. Well, we are. I don't think Northrop Grumman is. I don't think they are, dude. But that's cool, man. What type of Linux stuff do you do? I also have a famous utility for Windows debloat. And that's about it. Ah, cool. Yeah, everyone could use a little bit of Windows debloat. Am I right? Am I right? That's cool, man. Right on. Sweet. Maybe thrust is getting between that ball and socket, Tessie. It looks like that may have been what happened, but the thing is that that ball and socket is right at the throat where we're saying failed. So yeah, RM dash RF Windows System 32. Is it a new design? Yeah, it's a new design. It's a test, dudes. I wouldn't like it's a failure. I'm pretty sure they probably already know what happened, bro. So don't. It blew up. It's better if it does it here. Better if it does it here than
Activated.
better if it does it here than anywhere else. That's the best place for that thing to do that. So Northrop Grumman's going to adjust their analysis because it was clearly wrong, or just a little bit off. They're going to adjust it. They'll put it out on test end again and send it. They might do it on a little bit of a slower timeline than our buddies over at SpaceX, but whatever. All right, what's this link, Phil? What do you got? Oh, boy. Oh, jeez. Can we go back to talking about explosions? Can we go back to talking about explosions? It's really worth it to switch in 2025. Yeah. Anyway, Chris Sidestack, thank you very much for the raid, dude. Guys, Chris does stuff with Linux. I'm going to go over there and give Chris a follow if you guys don't mind. I'm going to go give my boy a follow over there. You should too. Technically, that was talking about an explosion. More recent explosions. Anyway, for the people that are over in Chris's stream, if you guys don't know me, I'm EJ. I do spaceflight commentary here, and I play spaceflight video games like Kerbal.
Oh, this is space. I'm in space.
Hey, yeah, you're on. Gifted a sub. I'm imminent flight. Imminent flight? Nice. Cool. No, I haven't, Ike. I haven't been out there. So I do commentary on spaceflight, which is what we're doing right now. I also work on my automobiles in my garage, and I play STEM games. Generally try to teach people something here over on Twitch. Use video games too if I have to. But anyway, yeah, that's what I do. Welcome in, everybody. The booster exploded. Yeah, it popped. That was not great. Yeah, you see part of it's there, part of it's over there, a little bit it's over there. My favorite part is whatever popped out in the back here.
T plus 110.
Watch. See that big explosion right there? Something came flying out of here, and watch right here. You could see a piece of it.
110 seconds.
Damn, dude, that thing got some distance. You see that thing, man?
Deluge.
Activated. Whoa. T plus 110 seconds.
Nice distance. Just a bit outside. Ball 4, ball 8. Have you heard of GPR edict? Or GP redict? No, I haven't. Competitive distance. Yeah, that drive must... now watch this. Now watch this drive. Now watch this drive. Derek, what's this? But anyway, we'll figure out what happens from Northrop Grumman here in a moment. If this is the Mark 1 Moonlander, I'm impressed. What do you say? Well, let me take a look. Do you think it counts as a home run? Oh, yeah. Background. Some of that. All right, Derek, what is this? It's a box. Oh, hey, I've been there. I know where that is. Neat. Oh, come on, Blue. You're not even going to show us what's in the box? You have to wait for Christmas? That's probably when they'll launch it. If it's a severed head, I'm going to be very upset. Cool. Cool. I wish they would show us what the hell it is. Yeah, I mean, that's about the size of their lander, Derek, so I mean, it looks about the size of a New payload fairing. Is that a self-propelled transporter? That's a COMAG. COMAG makes kind of bespoke SPMTs for specific applications. So yes and no, but yes, but no, but yes. Why didn't they mention the moon then? It could be a payload. But they said they're over the moon about this special delivery. I'm going to go ahead and say that that's their Mark 1 lander, most likely. It might be just a little bit short. Hey, Sitherly, 63-month resub. I'm not sure if it's that. Blue has shown pictures of... Yeah, I don't think it's... I'm not sure if it's that thing. It might be. It looks a little small to be the Mark 1. An SPT. Yeah, right. What does OPS and OPS and MFG, operations and manufacturing? Oh no, not the music. No. Yeah. It looks to be a little bit short, but that's because its landing legs could be folded up, so I think the Agalex, I think it's because the legs are folded, if I had to guess. But yeah, that's it's definitely Lorge. Lorge and in George. Cool. Huh. Fellas, that's absolutely the lander. Look at the center of gravity indicator. See that? See the little crash test dummy mark? That's your center of gravity indicator for moving this around. That's awfully low for anything. That's awfully low. Yeah, that's absolutely the lander. So look at where that is correlative to where the Mark 1 landing legs are. So if the landing legs are folded and retracted, and this part of the vehicle right here is sitting on the bottom, right? Your center of gravity is right there. Right? That's a fair distance up from the bottom of this. That seems to be right in line. Seems to be right in line. That's the lander. It's absolutely the lander. Let's beat SpaceX to the moon. I wouldn't rule it out, and that would be quite the boast for Blue. They're certainly going to try, dude. That's what I mean about, that's what I mean about not counting them out, dude. Well, there's doubters out there, like, why would you do it's just, like, same thing with Blue, same thing with SpaceX. Like, look at the hardware, dude. They have that big factory. You think that's just for making new Glens? Right? Like, not you. You know what I mean? Like, counting them out? What are you, crazy? What are you, nuts? Dude, they're going to do amazing stuff, and there's no doubt in my mind. Same with SpaceX. Best part is, as spaceflight fans, we can enjoy both of those things. That's the best part. That's the best part. So what if they beat them to the moon? That means we landed something on the moon. I ain't upset. SpaceX isn't pushing for the moon, but they are contractually obligated to NASA to land something on the moon and do it sooner rather than later. You're a cube, Bloodman. Got him. Got him. Any idea why SpaceX never messed with SRBs? SRBs aren't reusable, Ari. That's why. That's why SpaceX didn't want to do it. SRBs are great for power to weight, but they're not good for reusability. Even if you go and fish them out, You basically have to go ship them back to the manufacturer. The manufacturer has to clean them, and then they have to install a new liner and cast new propellant inside of it. That's not good if you want a high flight rate. Now, I will say this once, I'll say it again. And people, it's not good for like straight reuse, but if you built out the right industrial chain, reusing SRBs makes sense and could potentially be as low a cost to launch as like a Falcon 9 if you employ them in scale. So i.e. you make a lot of casings. It only really makes sense to recover SRBs if you're trying to do a high flight rate. And if you're trying to do a high flight rate, cost of manufacture goes down. SRBs aren't like necessarily reusable, and the turnaround time to reuse one is quite high. But the turnaround time is still preferable to making new ones, right? It takes a long time to manufacture these things, to manufacture those segments. Does this sound familiar? SRBs only really make sense if you're employing them in mass. And reusing them only makes sense if you're employing them in mass because they take a long time to make. So because they take a long time to make, you're going to have to make a lot of them, right? So you always have an SRB ready to go. You make a huge supply chain, right? Reusing SRBs makes the same sense. It could be potentially as cost effective as reusing a liquid booster like a Falcon and landing it, for the same exact reasons why SpaceX themselves are reusing fairings. Fairings don't cost very much. But if you want to achieve a high flight rate, fairings take a long time to make. So it was in SpaceX's best interest to reuse them. The shuttle program was supposed to do that with SRBs for the same exact reasons. SRBs take a long time to make. They're not particularly expensive. They take a long time to cast all the damn propellant inside of them. You have to basically let the propellant cure like casting concrete. That's how they cast segments, right? So SpaceX didn't want to dabble with that. They wanted to go with all liquid because they wanted to be able to turn around the boosters fast. That's not to say that you couldn't, right? You could scale, you could employ reusable SRBs in mass. You'd have to launch a lot though. And you could potentially be cheaper than Falcon 9 because an SRB has one moving part, technically two, the igniter and the thrust vector control. 2 axes, 3 parts, 3 moving parts. That's it. Dunking them in salt water wasn't good either. They're steel. Don't worry about it. They're marine grade steel. It's fine. The SRBs for the space shuttle program are made out of the same stuff that they make ships out of. There's a really good reason for that. Part of that was the reusability. Yeah, Aqualex, there's also that. That and you have an exceptionally large solid fuel logistics chain like we do for our ICBMs. So Aqualex, it's not as far-fetched of an idea as you might think because we're, once again, refurbishing our ICBM supply chain right now. Northrop Grumman got a disgustingly large contract, I forget, a couple of years ago to do exactly that. So there ain't no shortage of ammonium perchlorate, man. That's what I'm trying to say. Was Falcon 1 supposed to be reusable? I don't think so. Anyway. All right, guys. We ended up doing a gigantic space news segment because of the booster failure. So I think what I'm doing for the rest of the night is we're going out in the shop and getting some work done. Yeah, there you go, Meridian. That's a good point. Okay. Falcon 1 was supposed to be reusable with parachutes. Yeah, frankly, so was Falcon 9. Yeah. I have a few more links for space news. Want to send them? No. Creeper, I think I'm good for the day. We've been doing space news here for about 3.5 hours. They're all super quick ones, but all right. Yeah, no. Let's get back out into the shop. Have you ever been in space? No. Rocket Lab announced their next launch on Saturday morning, less than 48-hour turnaround for the pad. Nice, dude. Cool. Anyway, that was pretty cool. That was a cool rocket launch and booster test review. And your rails need steel it. That's right. Thanks for doing space news. It's great knowing what's going on in the industry. Absolutely, man. I would like to just close this space news with saying that everything that I said about what was going on with Northrop Grumman's booster is entirely speculation on my part, and I'm most likely wrong. Just a little bit of a disclaimer there. But we do know it failed. Yeah. It popped. Yeah, no, that was not supposed to do that. That's about all we know for sure, set in stone. That was definitely not intended behavior. But once again, dudes, Northrop Grumman, they'll figure it out. They'll figure it out. They're not stupid over there. They got Doug Hurley running the show. They're fine. They will be fine. All right. So I'm going to jog the YouTube VOD on the Twitch side of things. Just stay put here for a second. I'm just going to make my way back out into the shop. And, yeah, we'll go from there. Yeah, you're on. What's ridiculous about that is basically a big nothing burger, but hey, whatever. Okay. Stand by for lost signal from the office, as expected. Or just, not for Twitch. Well, kind of. I'll be right back. Don't go anywhere. We're starting soon. See, it says it there. Unless you're watching on YouTube VODs, and then we're stopping like right now. So just wait a second. We'll be live again in a second. In fact, if you're still watching the VOD, go click. See if I'm live. I'm probably live right now. Unless I'm not. In which case, wait an hour. Or 3. Or 6. You understand what I'm trying to say. I'll be right back.